In this video, we're going to introduce the basic ideas of electric circuits. This includes circuit diagrams like this one here, Ohm's law, and the Kirchhoff rules. So to begin with, let's just define a few key concepts. One is current. Current is given by the symbol I and has units of coulombs per second, charge per second. This is also called an amp. We define current as the number of coulombs of charge that flow through the circuit in 1 second, charge per second. So if you think about a circuit like this, you can imagine that you have charges flowing around the circuit, and what we care about is how many coulombs of charge move through the circuit every single second. That is our current. The other important new concept is called resistance. So resistance is given by the symbol R. It has units of ohms, which is also volts per amp. We'll get to where that comes from. And resistance, the basic idea is it is the resistance to the flow of electrical current. So the higher the resistance, the more difficult it is for charges to flow around that circuit. The idea that I have in my head about resistance is I think about a circuit as kind of like a road. So I have a road that's nice and smooth. This is a low resistance road where charges can move very easily around the circuit. It doesn't take much of a push to get the cars going very, very fast. And so this would be a low resistance and therefore fairly high current situation. Imagine that we made the road very bumpy and rocky and full of potholes. That is like adding resistance to your circuit, right? It is more difficult for cars to drive very fast down this very bumpy road, and that is a high resistance system. If you have a very bumpy road, you're going to have fewer cars per second able to drive down it, right? If we're on a freeway where every car can go 80 miles an hour, we're going to get a lot of cars per second around our loop. If we're on a very bumpy road, we are going to get many fewer cars per second able to travel around our loop because they just cannot travel as fast. That is kind of the best visual I can think of for resistance in a circuit. It is how difficult is it for electric charge, specifically electrons, to move around the circuit. The more resistance we add, the more difficult it is to move around that circuit. Okay. Specifically, we can analyze a circuit using something called Ohm's law. Ohm's law relates the current, voltage, and resistance for a circuit or for any specific element within a circuit, like a resistor. So the way that I think about this is current, how many charges move around my circuit every second, is directly proportional to voltage. Remember that voltage is the energy per charge, but it's also deeply related to the electric field. The higher the voltage difference between 2 points, the stronger the electric field between those 2 points is. So if I increase the voltage between these 2 points, I am applying a larger force to my particles. Therefore, they're going to go faster and I'm going to get more current. The resistance is like making the road rougher. If I make the road more difficult to travel, even if I'm pushing really hard, the cars just aren't going to go that fast. Adding more resistance reduces your current, means that you can have fewer charges every second moving through your circuit. So current is directly proportional to voltage because higher voltage means a larger force on the particles. And it is inversely proportional to resistance because resistance is attempting to slow the particles down as they move around the circuit. Now, rearranging this equation here, we can write it as resistance equals voltage over current. And this is how we see where we got the units for resistance. The omega, that is the unit, it's called an ohm, is volts per amp, volts per amp. So that's where we get the unit of ohms from. Now let's look at a specific example of using Ohm's law. With this circuit here, we have a 9-volt battery. This voltage represents the difference in electric potential between the positive and negative ends of the battery. So really what we're saying when we say the voltage of the battery is 9 volts is that this negative side is 0 volts and this positive side is 9 volts. And this should be delta V, but in general we are lazy and we just write V for the battery, which is the difference in electric potential between the positive and negative terminals of the battery. Okay, so we have a 9 volt battery, that is the V that goes into my Ohm's law, and I have a 1 ohm resistor. Now, the symbol for resistor is this squiggly line here, and a resistor could be anything that prohibits the flow of electric charge. It could be a light bulb, it could be a toaster, it could be something that is just called an electrical resistor whose only goal is to resist the flow of electrical charge. They are found within many electronic components. So what we are going to do is we are going to consider that there is this discrete resistor adding resistance to my circuit, making it difficult for the electric charge to flow, and that all of this connecting these smooth lines are perfectly conducting wire, which add no resistance into the circuit. So we can say all of the resistance comes from this one discrete chunk. This is not exactly true, but it is close enough to true for what we need to do. So using this, we can write our Ohm's law as I equals the voltage divided by the resistance is 9 amps. That is 9 coulombs of charge would flow around this circuit every second. Now let's take a moment to talk about the direction of current flow. So physics uses something called conventional current. This is basically that we assume that the current flows in the direction that a positive charge would move around the circuit. So current, which is what we will always refer to as I, flows from the positive terminal of the battery to the negative terminal of the battery, because positive charges move from areas of high potential to areas of low potential. That is the direction of the force on those particles. They want to move to the lowest energy state, so they move from high potential to low potential. Now, no particles actually move that way. The actual particles that are moving are electrons. Electrons feel a force in the opposite direction that positive charges feel, since they're negatively charged, which means that they flow from areas of low electric potential to areas of high electric potential, meaning they flow from the negative side of the battery to the positive side of the battery. You could think of it, say, there's a lot of electrons here, they're all repelled from one another and attracted to the positive charges, so they will move through the circuit to reach the positive charges on the other side. Now, the flow of the electrons is in the opposite direction of the conventional current, and those are the things that are physically flowing. This is the physical picture of what is happening in the circuit. Because of historical reasons, people chose the direction of the electric current to be opposite of this. I believe the story is that way back when they were developing these conventions, people actually didn't know about electrons or protons. They didn't know what was actually moving. And it turns out that it is tough to tell the difference between negative charges moving this way and positive charges moving in the opposite direction. So they just took a guess and said, okay, let's have positive charges moving in this direction, and the convention stuck. So we will talk about kind of magical positive charges moving from the positive terminal to the negative terminal. That is conventional current, and what I will call the direction of I. The real picture is here, but we will in general ignore this because these two pictures for everything that we are going to do are equivalent. Negative charges flowing this way are the same as positive charges flowing this way. Now we're going to discuss Kirchhoff's rules. Kirchhoff's rules are rules that govern the movement of charges within a circuit, and they're both fairly logical. So, the first Kirchhoff rule is that the change in electric potential around a full loop must be 0. One way I like to think about this is in terms of a ski slope. So if you think about the top of the mountain, the electrons or magical positive charges, because we're going to be thinking in terms of conventional current, so we have these positive charges that are going to be moving. So our skiers are like the charges, and they're going to kind of go in a circuit, taking the ski lift to the top of the mountain, skiing down the mountain, and back and forth. So if they start at the top of the mountain, they are at high potential energy and high voltage. Positive charges are at a high potential energy when they are at a high voltage value. They then lose that potential energy as they follow the force on them. Skiers move in the direction of the force of gravity down the mountain. Electrical charges move in the direction of the electric field, the electrical force on them, down the mountain. This is where we lose all of the potential energy that the battery gave us, and we use it to do some kind of work, right? So this could be lighting up a light bulb or running a camera or whatever it is. Then we end up at the bottom of the ski slope and we've used up all of that potential energy. We need to get it back, so we take the chairlift back to the top of the mountain. Every time you reach the top of the mountain, you have the same amount of potential energy as the last time you got there, because you're at the top of the mountain in the same place you were during your last cycle around, right? Every time you get to the bottom of the mountain, you must have the same potential energy because you're standing at the bottom of the mountain. And the same thing applies here. Every time I get to this location, I'm at 0 volts. My electric potential is at 0 volts. Now let's talk about the second Kirchhoff rule. The second Kirchhoff rule says that the current entering any junction must equal the current leaving that junction. That is, current in equals current out. The basic idea here is that if we have a point where our circuit splits, where we have some current entering a point, the total current entering the point must equal the total current leaving that point. I like to think of this as like a traffic example. Basically, if we have 3 cars that enter a junction, 3 cars must leave that junction. So they can split themselves in any way that they want, right? So say 2 of them go to the left and 1 of them goes to the right. But if we have 3 cars coming in, we must have 3 cars going out, right? And current is basically coulombs per second, which you can think of here as cars per second, right? So every second, 3 cars enter the junction, 3 cars leave the junction. In the way that this circuit is set up, 2 of those cars go left, 1 of those cars goes right, but we don't have any cars sticking around in the junction. And that's the basic idea. All of the current that goes in must also exit. Now let's consider our final Kirchhoff rule. Now, this rule is not an official Kirchhoff rule. You won't find it in the book, but I find it such a useful concept that I include it as one of my Kirchhoff rules. So you can write this down as kind of like a fake Kirchhoff rule, but it is very useful. So it says that any 2 points that are directly connected by a conductor are at the same potential. That is, the difference in potential between them is 0. So let's see how this rule applies to a real circuit. In this circuit, I have a battery here. The positive terminal of the battery is at a potential of 9 volts. The negative terminal of the battery is at a potential of 0 volts. This entire region that is colored in blue is connected directly by a perfect conductor. This is a wire. We consider our wires here to be perfect conductors. This is not exactly true of real wires. Real wires do have some resistance to them and are therefore not perfect conductors, but it's close enough for what we are going to be doing in this class. So these perfect conductors here do not have any potential drop across them. I'm 9 volts when I'm connected to the battery. I'm 9 volts right before I get to the resistor. Likewise, this part of the circuit colored in black here is all at a potential of 0 volts because it's all directly connected by a conductor. Now, what that tells me is that just to the left of the resistor, I'm at a voltage of 9 volts. Just to the right of the resistor, I'm at a voltage of 0 volts. And so I must have lost 9 volts. So my change in potential across that resistor as I move in the direction that conventional current would flow is negative 9 volts of potential difference. We will see that this rule becomes useful as we add more and more resistors and create more and more complex circuits. Now, another way to think about this rule is if we actually have an ideal conductor, then that ideal conductor has 0 resistance. Therefore, the voltage drop across some component, some wire that has 0 resistance, is the current flowing through the wire multiplied by the resistance is 0. So if I really have a 0 resistance wire, even if I have current flowing through it, I have no potential drop across it according to Ohm's law. Now that we've learned the rules for analyzing circuits, let's take a look at a slightly more complicated circuit. So this is what's called a series circuit. We have 2 resistors and they are in series. That means that all of the current that flows through one resistor must also flow through the other resistor. That is how we can tell that a resistor is in series with another resistor, if the currents between them must be the same. And this makes sense from a logical point of view. If I have some particle that is moving through resistor 1 here, which I've labeled as R1, the only way for it to get back to the battery is for it to move through R2. Therefore, every particle that moves through R1 must move through R2, and therefore the current through those 2 resistors must be the same. To see how we can analyze series circuits mathematically, we need to look at Kirchhoff's rule number 1 that tells us the total change in voltage around any loop must equal 0. Now, that tells us that the voltage provided by the sources, that is the battery, minus the voltage drop across the resistors must equal 0. That is, the voltage provided by the battery minus the voltage drop across the resistors must be 0. Now, if we move this to the other side, that tells us that the voltage of the battery, the positive voltage provided by the battery, must equal the voltage drop across the resistors combined. How do I know? Well, if I look here at my circuit, I start out at 10 volts at the positive terminal of my battery. At point B, I'm still at 10 volts. I drop some resistance, so there is some voltage drop across R1, where I end up at point C. I don't know the voltage of point C, but I know that it must be less than B because I have a voltage drop across a resistor. I get to point D, I'm still at the same unknown voltage, and then I have to lose the rest of my voltage here because at point E I have to be at 0 volts because I'm connected to the negative terminal of my battery. So between B and E, I had to lose a total of 10 volts of potential. Now, how much did I lose in the first resistor and how much did I lose in the second resistor? That depends on the individual resistance values, and we'll see how to calculate that shortly. Okay, so what we are doing here is we are setting the positive voltage of the battery equal to the voltage drops across the resistors. So in this case, we're going to consider these voltage drops to be positive. We're going to say, how much voltage did we lose? Well, we lost 10 volts. So the 10 volts provided by the battery equals the 10 volts lost by the resistors. Okay, so in this case, we can write down our voltages using Ohm's law. That is, the voltage drop across resistor 1 must equal the current through resistor 1 multiplied by resistance 1. Likewise, we can do the same trick for voltage number 2. Ohm's law applies individually to each resistor. If I know the current and the resistance of a resistor, I know the voltage drop across that resistor. So I simply can add up these voltage drops, and now I can simply remember that we said the current through the 2 resistors must be the same. That is, I1 equals I2, and I'll just call it I. This allows us to rewrite the total voltage drop across our resistors to be I multiplied by R1 plus R2. Now, we can also argue that the current through the circuit multiplied by the resistance of the entire circuit together, that is, the equivalent combined resistance of these two resistors together, must also equal the voltage drop of the battery. So we can argue that the sum of the voltage drops across the individual resistors must be 10 volts in this case. But likewise, that if I figured out, for example, the total resistance of these two resistors together, then the voltage drop across those combined must also be 10 volts. And if we could figure out what the combined resistance of those two resistors together is, then we could figure out, for example, the total current. Okay, for right now, we can see that the current through each of the resistors is equal to the total current, and therefore the total resistance must just be equal to R1 plus R2. That is to say that for a general series circuit, the total resistance of resistors in series is simply the sum of the individual resistors. Now let's use our knowledge of series circuits to actually find the voltage drop across each of these resistors and the current through the entire circuit. So first we can find the total resistance of the combined resistors using our series resistance rule. That is, the total resistance is the sum of the two resistances of the resistors individually, which is just 5 ohms, 2 ohms plus 3 ohms. Next, what we can do is we can say that the voltage, the total voltage provided by the battery, must equal the total current multiplied by the total resistance. So that is 10 volts equals the total current multiplied by 5 ohms, or we can solve for the current as being 2 amps. So in general, this is going to be a consistent theme for us, where we are going to, in a circuit, try to find the total resistance and then use that total resistance to find the total current. Once we have the total current, we can now build back up and find the voltage across each resistor individually. So if we want to find the voltage drop across the first resistor, well, that's just I1 times R1. I know that I1 is the same as the total current because all current flows through each resistor. So that is simply 2 amps multiplied by 2 ohms is 4 volts. Likewise, for V2, that can be I2 times R2 is 6 volts. If I add these two together, I get 10 volts. So the voltage drop across each of my resistors equals the total voltage provided by the battery as advertised. Okay. Now what we can do as well is we can find the voltage at individual points along our circuit. So I have these points labeled A, B, C, D, E, and F. So from A to B, there is no resistor, and therefore the electric potential does not change. The voltage doesn't change. So at point B, we must be at 10 volts. Then we lose 4 volts. So we're at 10 volts, we lose 4, we are at 6 volts. So point C is at 6 volts. Point C is directly connected to point D, so point D must also be at 6 volts. Then I pass along resistor 2, I lose the final 6 volts, so 6 volts minus 6 volts is 0 volts. And I am back at 0 volts to return to the battery, which I must be at 0 volts. If I am along this line here, I must be at the same potential as the negative terminal of the battery, which is 0 volts. Another type of common circuit structure is a parallel circuit. So a parallel circuit is set up such that the current leaving the battery has a choice of which resistor it goes through. In the series circuit, all of the current had to go through both resistors, but here any current that leaves the battery is able to go through either R1 or R2, but it cannot go through both. If it goes through R1, it ends up going back to the battery. If it goes through R2, it ends up going back to the battery. So it will not ever go through both of these resistors. What we know about a parallel circuit is that the change in voltage is the same across resistors in parallel. How do I know that? Well, I can use Kirchhoff's rule number 3 that any sections of a circuit that are directly connected by a conductor are at the same voltage. So all of this region over here, highlighted as purple, is at 10 volts because the positive side of my battery is at 10 volts and it's connected via a perfect conductor to all of these points, which means that the left side of my first resistor and the left side of my second resistor are both at a voltage of 10 volts. Now, this blue marked region on the right side, all of this region is at 0 volts. How do I know? It's connected to the 0 volt negative terminal of the battery. So the left side of both of my resistors is at the same voltage. The right side of the resistors is at the same voltage, which means that the change in voltage across each of my resistors is the same. This is our definition of resistors in parallel. They have the same voltage across them. So, something important to remember, parallel resistors share the same voltage. Series resistors share the same current. If you can remember that, you will easily be able to recognize series and parallel circuits. Okay, so now let's use this knowledge in order to analyze a parallel circuit, figure out the total resistance of two resistors in parallel, and then find the current, total current and the current through each of the resistors. All right. So in this case, we're going to use the second Kirchhoff rule, which is that the total current that enters any junction must equal the total current that leaves any junction. So here we have a junction where the total current from the battery comes in and I1 and I2 leave. So I total must equal I1 plus I2. We can turn this into V1 over R1 plus V2 over R2 by using Ohm's law. And we know that that must be equal to the total current, which would be the total voltage, the voltage of the battery, divided by the total resistance, right? So here are our individual I1 and I2 values. Here is our total current equation. Now, we know that each resistor has a voltage across it equal to the voltage of the battery. So V1 equals V2 equals the voltage of the battery, which means that we can pull V battery out on the left side and get this equation here. This is the equation for resistors in parallel. That is, 1 divided by the total resistance is equal to the 1 over the resistance 1 plus 1 over the resistance 2. Do not think that this is the same as the series addition rule for resistors. It does not work the same way. So let's try it out on our circuit here. We have two resistors of 2 ohms and 3 ohms. So the total resistance looks like 1/2, 1 over 2 plus 1 over 3. Adding those together, finding a common denominator of 6 gives me 5 over 6. So 1 over the total resistance looks like 5/6 ohms. So the total resistance looks like 6/5 ohms. Now, notice that this is smaller than either of my initial resistances. I started out with a 2 ohm resistor and a 3 ohm resistor. I put them in parallel and I got a total resistance of less than 2 ohms, just over 1 ohm in fact. This is a persistent theme of resistors in parallel. The total resistance of resistors in parallel will always be less than any of the individual resistors in parallel. The way that I think about this is the total resistance is how hard is it for a particle to move from the positive terminal to the negative terminal. When I add extra resistors in parallel, I am opening up new avenues for these particles to flow through. If I only had my first resistor, every particle would have to go through this one resistor. But if I add another one in parallel, now any particle has the option of going through resistor 1 or resistor 2. So it's like opening up new lanes in a freeway, right? If I only have one lane, then there's more traffic jams. It's harder for more charges to move through only one path. If I add on new paths in parallel, then I am reducing the resistance. It is easier for those particles to move. My total resistance will be less. So we can now find the total current through this battery, which is equal to the voltage of the battery divided by the total voltage here, which looks like 10 ohms over 6/5 ohms, which is 25 over 3 amps. So that is going to be just over 8 amps of current. So if we remember back to our series example, I had a 2 ohm resistor and a 3 ohm resistor in series when I only got 2 amps out of it. That is, the current through my circuit in series was only 2 amps. And now I put them in parallel, my resistance is much lower, and I get a much higher current because it's easier for the charges to flow through this parallel circuit. As a quick review, in this video we learned about Ohm's law, we learned about the 3 Kirchhoff rules, 2 of them officially found in the book and 1 of them very useful. And we learned about series and parallel circuits and how we can find the total resistance of resistors that are in series and in parallel.